In this module, we will talk about semiconductor packaging past, present, and future. In this section, we will cover Moore's Law, a brief history of packaging, and packaging future trends. In 1965, Gordon Moore, who is actually later the co-founder of Intel, made a simple observation. The number of transistors will double every year. Later, that was updated to every 2 years. And that the cost per transistor will reduce every time it scales, every time a new node is created. This is Moore's Law, and believe it or not, it continues to hold today. So what that means is feature blocks are shrunk and multiplied, which gives more compute every node. You can add more feature blocks, which is improved capability every node. And then the smaller silicon die can be made, which is reduced cost. With the scaling of the transistor, then the computer evolved. Back in the 1960s, it was one computer serving thousands of users. Then it became thousands of computers in today's era serving one user. Semiconductor packaging also needed to scale. So at the creation of the first IC chip in 1959, packaging started with invention of the first package in 1964. So in the 1970s, packaging was done with something called a dual inline package, a DIP, that used wires to connect to bond pads on the silicon to a substrate frame. These were very low pin count devices, say around 60 pins. And pins are those little legs sitting out of the bottom of that dual inline package in that first picture. In the 1990s, flip chip was invented. So now instead of using wires to connect the silicon bond pads to the substrate, solder balls were used to connect the IC to the substrate. Whereas wire bonds could only hit pads at the edge periphery of the silicon die, now we were able to use the full surface. So a lot more pins accessible to connect to the substrate. A ball grid array package was invented. This allowed the surface mount industry of soldering packages directly to the motherboard rather than sticking pins through the motherboard and using something called wave soldering. And pins increased, went to now 500 to 1,000 pins coming out of the package. In the 2000s, a big transition happened in the industry to lead-free due to the hazardous nature of leaded solder. Packages got cheaper through organic substrates rather than using ceramic, went to plastics, and they got smaller because phones started coming into the industry and miniaturization was very important. Now we're talking about packages with many thousands of pins, and we're also having packages run at very high frequencies that needed cooling and thermal solutions to get all that heat out so they could run super fast. Now in the 2010s and 2020s, we have advanced packaging. So this is way, way beyond just containing the chip and doing that micron to millimeter dimensional hierarchy scaling. We have heterogeneous integration. So we're combining many chips, multiple chips on one substrate, connecting chips together on a silicon interposer. We're incorporating other devices into the package like memory, and even putting silicon inside the substrate so we can have very high speed, high bandwidth connections. And some packages moving away from copper traces to connect to the system to photonics using light instead, much faster and higher bandwidth. So in the 1970s, a CPU had around 2,000 transistors. Now, today's packages have billions of transistors. So you can see packaging is a critical part of the semiconductor device process, and advanced packaging has much more innovation to happen. Now, if we look at the next generation of packaging trends, we have to, number one, keep the package features scaling to support shrinking transistor sizes. Remember, Moore's law continues to scale. Transistors get smaller, more transistors on the same silicon die size. We do still need to shrink packages to enable more packing of devices in compact systems, so put more content, more packages in that phone, for example, and continue drive this heterogeneous integration for higher functionality. This picture shows really what this goal looks like. Imagine a PCB has long traces that requires lots of power to send signals, a large form factor, large XY, large dimensions, so it takes up a lot of space, and coarse features. So you cannot get high bandwidth. You can only put so many traces per millimeter because of those coarse features. So we go to on-package integration. Now we have shorter distances, so you need a lot less power. You have higher speeds because your feature sizes are a lot better and you can pack in more traces per millimeter and get higher bandwidth. And now we're putting in many devices, so it has more functionality. And basically, this future looks like taking parts of that motherboard, parts of that system, and converting it to the package. So in summary, Moore's law projects that the transistor count doubles every 2 years with increasing performance on every node and reducing cost. Packaging has advanced significantly since the lead frame package, and now we're in the phase of heterogeneous integration, which enables packages to have a lot more functionality. Thank you for watching.